Hi, this is Isaac Higgins, reviewing my second out of 3 research papers for the course Engineering Self-Adaptive Systems. The second paper is called Machine Learning Meets Quantitative Planning, Enabling Self-Adaptation in Autonomous Robots. It was written by Pooyan Jamchidi from the University of South Carolina, USA, Javier Cámara from the University of York, UK, and Bradley Schmerl, Christian Kastner, and David Garlan from Carnegie Mellon University, USA. This paper was written in 2019. Regarding systems that are configurable and can have many different attributes as part of that configuration, self-adaptive robotic systems may alter that configuration as obstacles appear and environments change. The main problem this paper is attempting to address is that currently, to choose an appropriate configuration, the self-adaptive system must come up with a plan. And although planners can be used to decide the best way to adapt the configuration at runtime, if the system is highly configurable, the configuration space is exponentially large. This means that planning is intractable or difficult to accomplish due to the size of the adaptation space. For example, if a robotic system detects the remaining battery power is too low to fulfill the goal or meet the destination, it may alter the configuration of the system, but in computing the best configuration to use, the power left may decrease significantly due to the computation needed to consider all the possible configurations available. Also, this method relies on accurate estimation of energy consumption. If the energy demand for a configuration is higher than expected or predicted, the robot could run out of battery earlier than anticipated. Although there are many self-adaptive systems out there in robotics that are able to adapt to new obstacles and environments, they adapt in a way that is either time-consuming, computationally intensive, or are inaccurate and still unable to perform the given task exactly as desired, even when uncertainty is presented to the system. There are 2 reasons this is still a problem today. The first is that there has not been a huge need for 100% reliable self-adaptive robotic systems, and the second is that there may still be a lack of trust from humans in what the robotics may be capable of, potentially in terms of large equipment in a self-adaptive context. The majority of work referenced in this paper regarding configuration optimization has been written by either all or some of the authors of this paper. This includes that several models, sampling strategies, and optimization have been used for performance optimization of highly configurable systems. In regards to the planning component of this paper, there exist approaches on finding solutions to adaptations based on planning and constraint solving, as well as statistical techniques that have been used for providing guarantees in self-adaptive systems with focus on real-time constraints and continuous learning. Lastly, there are studies that use machine learning to support decision-making, all of which are either black box models or suffer from scalability restrictions, where the adaptation space did not get larger than 1,000 alternatives, and the approach tested in this paper consists of over 1 million configurations. The main goal of this entire paper is to enable self-adaptation in highly configurable systems that operate in dynamic and uncertain environments, using configuration change as a main mechanism to enact adaptation. The key to making this happen is to overcome the size of the configuration space, the number of possible configurations, by finding a configuration that provides a suitable adaptation for a situation at runtime. And it is expected that not all configurations are important to consider. This can be achieved by, instead of searching through the whole configuration space, exhaustive search and machine learning can be utilized to find the most desired configurations more efficiently. This will in turn optimize the configuration finding for any required adaptation at runtime. This is a better solution because instead of having to expand resources in trying to find the best configuration for an adaptation in any given environment and situation, whether to reduce battery consumption and efficiency or to improve performance using configuration optimization, planning and machine learning, many configurations can be ruled out and only consider the Pareto-optimal configurations. Pareto-optimal configuration means a configuration that has 80% of the desired attributes, but only requires 20% of the time to acquire. These Pareto-optimal configurations are found using a machine learning algorithm outlined within the paper. At the start, the authors had two hypotheses. The first was that machine learning could find optimal configurations without exploring all configurations, and the other was that restricting online planning to search only Pareto-optimal configurations would lead to tractable runtime, not so difficult runtime planning that would still result in high-quality adaptation plans. To evaluate these two hypotheses, the authors designed and ran two experiments. The first was controlled in a theoretical setting with a large configuration space that was validated on the real system to increase internal validity. And the other experiment used independent evaluation on a robotics scenario that was described earlier on in the paper. For the first hypothesis, the experimental evaluation, the results were also compared with classification and regression trees, because in previous literature, it is a popular machine learning algorithm. The authors touch on the threats to the validity of the results. This includes internal and construct validity and external validity. The internal validity mentions that the evaluations were conducted independently by a third-party evaluator without any intervention from the researchers. And the external validity mentions that the results must be interpreted in the context of a robotic systems only. The only critique I have for this paper is that there was not much written about why this problem still exists today. As the reader, I had to half guess from what the problem was, why it was the case, and why it had not been covered in literature already. Thanks.